Oh, cool.
Yeah. I thought it was going to stop.
Yeah, I've never seen it like that. Where did you find it?
Online. On half like eBay's book source.
So there is a hardcover version of this book. If anybody's interested, I guess it can possibly be found on the internet if you're lucky.
I think I paid $45.
So I wanna start by making a couple of announcements. The first one is I didn't realize when I assigned the homework that the Monday that I made it due is a holiday. So that means that the homework is actually going to be due on Tuesday for you guys. So that means either. Well, actually, let me leave it up to you guys. So the reason that I wanted to make it due before Tuesday is because Tuesday is drop date. So it's your last chance to know if you're staying in the class or not. So that's why I wanted to make it due Monday so that you could get a feeling for what the first homework did and what it's going to be like. I can see how maybe if it's due Tuesday, then maybe some of you are not coming on Tuesday because you're on a Monday, Wednesday, Friday schedule. I'm perfectly happy to make the homework due on Wednesday. But you guys are aware that Tuesday is drop date. So does that sound fair? Does that sound good?
And it's due by midnight on Wednesday?
So it's going to be either due Wednesday. If you're going to turn it in paper, then in class. And if you're going to give me a LaTeX PDF, then you can email it to me.
Either way you want.
By midnight.
A PDF, or you want a typed LaTeX version, whether we turn it by hand or by email.
So I'm offering a 10% LaTeX incentive. So
Oh,
yeah, so you don't have to type it up, but it's good for you. So the PDF is what I want, not the text file. And the other thing that I wanted to tell you is, so somebody asked me where am I in the book, basically, you might have seen that chapter 0 is kind of motivating the course, but if you try to read through it, you'll find that actually you don't know a lot of the definitions yet. And so what I'm doing is really, I've started the course at chapter 1, and I keep going back to things from chapter 0 as motivation, So the proofs are all coming from chapter 1 so far. But when I talk about examples of polytopes, things like this, you can find that in chapter 0. And basically, that's what I'm going to keep doing is start at chapter 1. I'll keep you posted as to where I am in the book. And chapter 0, I basically skipped, and we're going to be going through it as the material goes on. Okay. Any other questions? Okay. So we're in the middle of proving the main theorem for polyhedra. Rather, the main theorem for polytopes, which basically says that a V-polytope is the same thing as an H-polytope. Okay. Or maybe let me say it like this. So the main theorem for polyhedra says this. Says that B polyhedra are the same thing as H polyhedra. And remember that a polyhedron is basically the analogous thing of a polytope when you allow it to be unbounded. Okay? And then, if you want the one for polytopes, then you just have to say that the V polytopes, which are the convex halls of finite sets, are the same thing as the H polytopes, which are the same thing as, I guess I haven't yet officially defined what an H polytope is, but I define it to be a bounded H polyhedron. Okay.
Do you require the intersection of the half spaces finite?
Yeah, so I spelled it a little bit further, but last time. But yeah, these guys have a finite number of vertices and rays, and these guys have a finite number of inequalities. So last time, I proved this direction, that every V-polyhedron can be described as an H-polyhedron. And so today, what I want to start by doing is proving the other direction, okay? And I'm going to just give you a sketch of the proof in the special case of H-polytopes, okay? But that contains all the main features. Okay? So here's what I'm going to do. I'm going to say, okay, let's consider an H-polytope. Yep. I think what happened is that last time I wrote H here and V here. So that's why you're confused. Wait, let's switch it around so that we don't get confused here. So I guess last time I proved this direction, and this time we're going to prove this direction. Thank you. So I'm going to take an H-polytope. Be an H-polytope. And remember that is described by something like this. So these are the points in R to the D such that A times X is less than or equal to Z. These are the linear inequalities that describe my polytope. And now I have to show you how I can make a V description out of this. How do I express this as a convex hull? Okay. So again, I'm gonna start with a similar trick as last time. I'm going to define an auxiliary polytope, a bigger polytope, and this is going to be the polytope of all points of the form X, Y in R to the D plus N such that AX is less than or equal to Y. Okay. And
all the X is the same.
the X is symbolizing the same thing, and basically Y is a variable that I'm putting here for Z. So maybe one thing that I should clarify here is that I always find it useful to draw a little sketch of the matrices I'm multiplying so that I remember what size they are. Okay? So A is meant to be a D by N matrix, and an N by D matrix, because I need to multiply it by my column vector X, which is in RD, right? So an M by D times a D by 1 is less than or equal to an M by 1 matrix. I would advise that you always draw these pictures when you lose track of what's of what size, what's dimension, what's number of inequalities, and so on. So for example, here we're describing a d-dimensional polytope, and there are n inequalities, right? Every row says, something is less than something. Something is less than something. So there's n inequalities describing, okay? And so basically now I'm making X to be representing this and Y to be representing this, okay? What I'm going to do then is note two things. So the first thing that I want to notice is that what happens when you intersect Q with the subspace where so I'm taking Q and I'm intersecting it with this, and this is a subspace. Why is it a subspace? Because I'm considering the points in R to the D plus N satisfying these equalities, that Y is equal to Z, okay? Well, you see that if you force y to be equal to z, then what you're going to get is the points x, z, and r to the d plus n such that ax is less than or equal to z. Okay, so you're basically going to get p if you force y to be equal to z. Why do I put quotation marks here? Because p lives in r to the d, and this guy lives in r to the d plus n. But they're basically the same polytope. It's just that I'm putting a, for each point p in here, I'm just appending a vector z, a constant vector in the bottom. But they're basically the same polytope. Yeah.
Now that you're multiplying an n by d matrix by a 1 by d matrix.
This is n by d, and this is d by 1.
Oh, this is d by 1.
Yeah. So that's the first observation, that I can obtain p by just intersecting this bigger polytope q with a subspace. Okay, that's the first observation. And the second observation is that I'm going to show that q is a V-polyhedron. Okay, this is not obvious, but I'm going to show it. And so then what I'm saying is that P is the intersection of a V-polyhedron with a subspace. Okay, and so what I'm going to show, so maybe I should say steps. This is the first step, this is the second step, and then the third step is going to be to show that a V-polyhedron intersected with a subspace is a V-polyhedron. Okay? And so if I show these three things, then I'm going to be done. I'm going to have shown that P is a V-polyhedron. Okay? So out of these three things, the first one, there's really not much to say. The first one is true by inspection. And so I'm going to show the second one and the third one. Okay? I'm going to show first that this thing Q that I defined there is a V-polyhedron, so I need to express it as a convex hull plus a cone. Okay? So it goes like this. So this is Q, and now I want to observe that if y is bigger than or equal to ax, that means that instead of writing y, I can write something like ax. Let me use the same notation that I have here. I guess I'm not using the same one. But, if y is bigger than or equal to ax, then I can write y as ax plus p, where p is greater than or equal to 0. But then what I'm going to do is I'm going to write this as ax plus 0p. From here to here? So I'm just saying if y is bigger than or equal to ax, then I'm just calling y minus axp. So I write y equals ax plus p, and this translates into this. Okay, so p is kind of an auxiliary variable. P is just y minus ax. And so I have it written like this. And now what I want you to notice is the following thing. That let's say that I write. So again, let's think about the sizes here. So x is in R to the d. X is a column vector of length d. So let me write it as x1 up to xd. Okay. Or I could also write this as x1 e1 plus xd ed, where the ei's are the unit vectors. Okay. So those are just the coordinates of x. And similarly, p is a column vector of size n. And so let me just write it as p1 up to pn. Or if we prefer to write it like this, I can write it as p1 f1 plus up to pd p n fn. Where, well, like I said, e1 up to ed are the unit vectors in R to the d, and f1 up to fn are the unit vectors in R to the n. Okay. And then what I'm going to do is that I'm going to say the following thing. I'm going to say so I just write out ax according to my expression here. And so what I get is this. Okay? So I just substitute x for what I wrote there. And then I'm going to say the following thing. I'm going to say I can pull out x1 because x1 is just a number, right? X1 is just the first coordinate of x. So that means that I can pull it out of this matrix and write it as E1, A1 like this. And so what I get is this. Okay? And so you see what I did is that I took my x, ax, and I'm writing it as a linear combination of this thing up to this thing. Okay? So in other words, this what I'm writing here is in the span of these things, E1, AE1 up to ED and AED, right? Because there it is. It's written as a combination of these things. Okay? And this is more or less what we want. But remember what we're after is we're trying to express this Q as a V-polyhedron, right? And what that means is that we want it to be something that looks like a convex hull or a cone. And what we have is something like a span. Okay? So how can we turn a span into a cone? Well, the thing is that when I take the span of a bunch of things, I'm saying take linear combinations of these things, but don't care if the signs are positive or negative. Right? These are just the linear combinations of these guys. I want a cone, and in a cone I'm only allowed positive coefficients. But so what I'm going to do is I'm going to just do this little trick where, you know, I'm going to take a combination of these guys, and then if the coefficient of this is positive, then that's good. I write it like this. And if it's negative, I just put a minus in front of it. and I do it like this. So if I'm going to take a constant times this thing, then it's either a positive constant times this or a positive constant times this. And I do that for each one of these guys. I'm turning a span into a cone. And I think it's probably worth it if I draw a geometric picture of what I'm doing here, which I think might be clear if you prefer geometry. If I look at I don't know, here's V1 and V2, okay? Then, but now it looks like this is a part of the span. So if I have something like the span of V1 and V2, then I'm saying that, if this is V1 and this is V2, then I take all possible linear combinations and that's the whole plane, right? All the possible linear combinations of V1 and V2 are the whole plane. And now what I'm saying is that if I now take my V1 and V2, you see, if I took the cone of V1 and V2, that would only cover this part, which is not the whole plane. But if I now allow myself to throw in minus V1 and minus V2, then all of a sudden the whole plane can be expressed as a positive combination of V1, V2, minus V1, and minus V2. If you're here, you write it as a positive combination of minus V1 and V2. If you're here, it's a positive combination of minus V1 and minus V2. And if it's here, it's a positive combination of V1 and minus V2. But I need to throw in the negatives for this to work. Okay. So I'm just saying the span of a bunch of things equals the cone of them and their negatives. Okay. And that's good because now this is starting to look like a V-polyhedron. At least this part is in this cone. Okay? Now let's look at this part. Here I had my vector written as xax plus 0p. And if you look at p, p is greater than or equal to 0, right? And so that means that 0p is in the cone of the positive unit vectors, which I called f here. What I'm saying here is that I can write my vector p as a combination of my unit vectors f1 up to fn. But not only that, because p is greater than or equal to 0, that means that all the coefficients are going to be greater than or equal to 0. Okay? Which means that this is really in the cone of all these guys. So this is a non-negative combination of these. And so when all is said and done, what I have shown is that Q is, I'm taking some element of Q and I'm showing that it's in the cone of all these things. Right? It's in the cone of these and these. Okay. So I took a generic element in Q and I expressed it as a non-negative combination of all of these guys. Okay. And so that shows that Q is contained in this cone. Okay? But I actually claim that Q is not only contained in this cone, it actually equals this cone. And that's something that is actually fairly easy to check. How do you check this? Well, you just check that each one of these guys is containing Q. And if each one of them is containing Q, then their cone has to be containing Q, because Q is a polyhedron. So this is one of these exercises that is good for you to do. That's going to be on the forum. Okay. But then what that means is that Q is equal to a cone. In other words, Q is a V-polyhedron. Okay. So this is a bit of a messy computation, but let's go back to the beginning and see where we are so far. Okay. Question? Okay. So just to remind you what we're doing, we started with an H polytope, P. We want to express it as a V polytope. And I said, okay, let's build this bigger polytope Q. And I showed that Q intersected with the subspaces P, and I just showed that Q is a V polyhedron. So to finish the proof, now what we need to show is this step number 3, that if you take any V polyhedron and you intersect it with the subspace, you're also going to get a V polyhedron.
I guess my question was, isn't the definition of a V polyhedron is that Q has to be a cone plus a polytope?
Right. So the definition of a V polyhedron is that it's a cone plus a polytope, and that means that if you're a cone, then
Plus the trivial polytope.
cone plus the trivial polytope. The trivial polytope being a single point. Okay. Okay, so that's the first part of the computation. And now let's do the second part of the computation. Okay. And again, I'm going to... One thing that I should point out is this, that if I show that V polytope, well, so that I'm going to make the simplifying assumption for polytopes. I mean, this is also true for polyhedra, but I'm going to do it for polytopes. But like I said, this contains all the main features. So that's my first simplifying assumption. Okay. My other simplifying assumption is that I'm going to do it for a subspace of dimension d minus 1. Okay? And why is that? Well, because intersecting with a subspace of lower dimension, you guys know that if you have a subspace of a lower dimension, that can always be expressed as an intersection of subspaces of a bigger dimension. Let me put it in a different way. If you have a subspace, and this subspace is described by k equations, then each one of these equations defines what's called a hyperplane of dimension d minus 1. And so and then if you intersect the hyperplane of each one of those equations, you're going to get your subspace. And so instead of intersecting with the whole subspace, we can intersect with one hyperplane at a time. Okay? So this is what's called a hyperplane. And let me ask you guys, if I force you to choose a favorite hyperplane in R to the D, which one would you choose? In R to the D. So what's your favorite hyperplane in R to the D?
The one.
Yeah.
The one that contains the unit simplex.
So you have a different favorite from the rest of us. So, right. So I'm hearing basically the same suggestion, except yours is different. Which is just you could just look at the one where the last component is 0, for example. Okay. So the equation is x sub d equals 0. Or maybe my favorite is the first component. So my favorite hyperplane is x1 equals 0. Okay. And that's the one that I want to intersect with. And the point is that if you have some other hyperplane, then actually you can do these things you do in linear algebra. You just do a change of basis and make your hyperplane be the hyperplane that you prefer. Okay. So in other words, what I'm going to show is that if I take a V-polytope in RD and I intersect it with the hyperplane where the first coordinate is 0, I'm going to get a V-polytope. This is what I'm claiming. And if I show you why this is true, then I mean, like I said, in the book this is spelled out in all the gory detail, but by looking at this example, you'll see all the main features. By looking at this instance, you'll see all the main features. So how do we do this? You have some V-polytope, okay? So maybe it looks like this. And when we say V-polytope, what we mean is that it's being expressed as a convex hull of points. Okay. So this is V1, V2, V3, up to Vn. Okay. And now I'm going to intersect. So I'm drawing a two-dimensional picture, which then means that when I bring in my hyperplane, well, if you're in 2 dimensions, then a hyperplane is just a line, right? And so let's say that the line looks like this. So this is R2, and this is where x1 is equal to 0. Okay? And you can imagine that here are maybe the coordinate axes, and this is x1, and this is x2. So that's why this is the line x1 equals 0. Okay? And so when I intersect my V-polytope with my hyperplane, what I'm trying to describe basically is this right here, right? This line segment. Okay? But I want to describe it as a convex hull. And so in other words, what I want to say is, it's the convex hull of this point and this point. Okay? How would you describe this point?
That's the convex combination of V1 and Vn.
It's basically the convex combination of V1 and Vn. In other words, the point on the segment V1 Vn that lies on this plane, on this line. Okay? And that's basically what we're going to do. We're going to do the following thing. We're going to say, actually, I want to relabel things a little bit, just so that it agrees with what I wrote here. Let's label. So let's say that P is equal to the convex hull of V. Okay. So V are the vertices of my polytope, and I want to write V in the following way. Let me say that the points above the hyperplane I'm going to call V1 up to VA. Okay, so So V1 up to VA are the ones that are above x1 equals 0. Okay. Let me say that the ones below I'm going to label with a W. Okay. W1 up to WB. You can imagine that here there might be more vertices. Right? And finally, let me call any points that land on the hyperplane, I'm going to label with Y's. Okay? So in this case, I just have one, which is called Y1. So what I'm saying is that these guys have first coordinate bigger than 0. These guys have first coordinate less than 0. And these guys have first coordinate equal to 0. Okay, so I split my vertex into these 3 types. And then I'm going to say something very simple, which is that the only points that have the chance of being a vertex of this guy that we're trying to describe, this red thing is what we're trying to describe. And I'm going to say that, so let's call it maybe Q. Okay. And so what I'm going to claim is that the only guys that have any chance of being a vertex are either the Y's, okay, the vertices of my polytope on this line, or they have to be points of intersection between a VI and a WJ. So the segment VI WJ intersected with that hyperplane. Okay. So what I'm going to do is that I'm just going to draw all those possible segments from a VI to a WJ. Okay. Like this one, like this one, like this one, like this one. I'm going to see where each one of those guys intersects my hyperplane. Here, 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 and here. And then I'm going to say, among that set, I must have the vertices of my polytope. There's no question about it. Okay. That's the strategy. So I'm going to define, for each VI and WJ, I'm going to say that the intersection of VI, of the segment VI WJ with the hyperplane x1 equals 0 is going to be a point which I'm going to call, what did I call it here? I call it UIJ. So, for example, this is U11, this is U1B, etc. Okay. And then my red polytope Q, the one that I'm trying to describe, remember I called it Q, is the convex hull of my points Y and my points U. Okay. So Y I, where 1 is less than or equal to I less than or equal to C, and the points U, I, J, where 1 is less than or equal to I less than or equal to A, and like this. Okay. So I'm writing an equation what I just described in words. Okay. Any questions about this? Okay, and then basically it comes down to proving this. Okay, so one direction is very easy. The direction that the right-hand side is contained in the left-hand side by construction. Yep.
Is there a definition of vertex one-dimensional spaces?
Actually, I'm being a little bit loose in what I call vertex because I haven't even defined what a vertex is. What I have said is that my V-polytope is a convex hull of a bunch of points. But if you look, for example, at what I'm saying here, I'm saying look at the convex hull of these 5 points. So the convex hull of these 5 points is the polytope that I'm trying to describe. But you would agree that that only 2 of those are vertices and the other 3 are not.
In this dimension.
In this dimension.
In higher dimensions, do we know that those are the only possibilities of vertices for that convex set? I guess is my question. Do we need to show, in general, that those are going to be one dimension?
We need to show it, right? So this is why I said I cling. So in this picture, it looks clear, I think. And what I'm saying is that this does hold true in general, but I mean, nothing is obvious when you go to higher dimensions. But so let's see. So the fact that the right-hand side is contained in the left-hand side is pretty easy. The reason being that if you look at any of these points, either the yi's or the uij's, then, by definition, these points yi and uij, they are inside the polytope P. And they are on the hyperplane, again, by definition, because they were defined to be intersections with a hyperplane. So if you're in the polytope and you're on the hyperplane, then you are in Q. So that means that each one of these guys is in Q, and therefore their convex hull is in Q, because Q is a polytope. So this part is not difficult. The other part is the part that is trickier. And it's exactly your question. So how do I know that these are enough to, these points that I defined here are enough to generate the whole intersection Q? How do I know that there's not other vertices that I'm not seeing? And the way that you prove this goes something like this. You consider a point Q in this intersection Q. Okay. And then you know 2 things. You know that Q, by definition, it's a linear combination of the points in V, right? So it's a linear combination of the V's, the W's, and the Y's. Where I have A V's, I have B W's, and I have C Y's. And I know that the sum of the coefficients has to be 1, and all of these guys have to be greater than or equal to 0. Okay. This is one thing that I know. Q being in P has to be of this form. Okay. And the other thing that I know is that because Q is on the hyperplane x1 equals 0, that means that when I take the first coordinate of this thing, I'm going to get 0. 0 is equal to the first coordinate of Q. Okay. And so I get I just take the first coordinate of these guys, and of these guys. And remember that the point is that these guys are positive, right? Because these are the guys that have positive first coordinate. These guys are negative. These are the guys that have the negative first coordinate. And these are 0, which means that this is not here. And then what you have to do is say, okay, well, you wrote Q in this form as, as sum of the VI's plus a sum of the W's plus a sum of the Y's. And then you have to rearrange this sum in such a way that instead of writing it like this, you transform this into, you basically say something like this. These linear combinations, basically I can write them as something like some constant ij times those guys that I have here. I can basically take this, and remember that uij, because uij is on the segment between vi and wj, that means that uij is a combination of vi and wj, and you basically take this and you rearrange it to look like this, which takes work. This is but this is how you do it. You start with this expression, and you turn it into an expression that looks like this, which shows that Q is actually a linear combination of the uij's and the yi's. And again, I think these are the kinds of details that if I just try to spell this out on the board, I'm gonna make a mess and put you to sleep. And this is the kind of computation that you have to do it and convince yourself. But this is basically the steps of that proof. Okay. And with the steps of that proof, I conclude the main theorem for polytopes. So what do we make of this main theorem for polytopes? I think you'll agree that the proof is maybe much more work than you might have thought it would be, because the statement itself, at least in 2 dimensions and 3 dimensions, the statement makes a lot of sense. It turns out that if you want to prove this in higher dimensions, you have to work hard. It's just, there are several different proofs, and this is the simplest that I know, and it's not simple. There's work to do. Okay. One thing that I should say about this is that implicit in this proof is actually hidden an algorithm to actually do this. If you really have a polytope that you're interested in, and you want to go from vertices to inequalities or from inequalities to vertices, it's going to take work. If you have a 10-dimensional polytope and you have the vertices, it's not clear a priori how to turn that into inequalities, and this is an algorithm that actually can be optimized. And if anybody's interested in these kinds of computational issues, the computation starts here, but you have to work even harder to make it go fast, so that the algorithm actually terminates. The really good news for you guys is that actually there's a program that is really good at this, and so you would never really have to do this by hand. You would never have to carry out these computations by hand. And something I'll say more about this program later on in the class, but it's very important that you're aware of it. It's this program Polymake. I think one day we should do a Polymake tutorial, because this is a program that is really good at dealing with polytopes. One of the things it can do is go from vertices to inequalities, but it can do a lot more. It can draw pictures for you. It can compute number of facets, number of faces, and all these kinds of things. Okay? Yeah.
I think it's really beautiful that this is a constructed proof.
Mm-hmm.
But it's also kind of interesting that in both directions, when we take some arbitrary dimension, we have to lift to a higher dimension both times in order to solve the problem.
Mm-hmm.
It seems like we're making it more complicated, but in essence we're not.
Yeah, I mean, it is true in both proofs. Somehow we were living in a certain dimension, and the trick in both directions was to just go higher into some kind of polytope that is, it's in a higher dimension, but that makes it simpler. So instead of having a complicated polytope in d dimensions, we go to a less complicated polytope in higher dimensions. That's basically the main idea of the proof. And then we have to work hard and do it. Okay, the rewards are done. We know this, and this is I mean, we didn't do all the work, but we did basically all the work. And now you have the main theorem for polytopes. You can go back and forth. This is going to be a very useful tool to work with. Okay. So I think I'll stop there for now. I want to say a word about the homework actually, because I think that now that you looked at the homework, you're probably realizing that I wasn't kidding when I was saying that some of the questions are hard. And what I should tell you about it is that there are some questions where no matter how hard you look in this book, you're not going to really see the light there. And I mean it that it's important that you guys work together, and it's important that you come talk to me and ask me for hints, because you know, what I want is for you guys to work it out, is not to give you something really hard that you cannot do. There are questions that they are hard, and I want you to work hard at them and solve them. And come talk to me. I'll give you hints. I'll help you out. In particular, questions like number 1. I think number 1 is a question that is hard to get started, and I'm happy to give you hints and then more hints and then more hints. But what I want is for you guys to succeed in the class, and I really mean that. And but I also want you to work hard, and I think the harder you work, the more you get out of it. So do that, and yeah, we can talk about the I guess the disadvantages that we're not going to have office hours on Monday. But on Friday, let's talk about these questions. I'll help you out.
Homework due Tuesday or Wednesday?
Homework is due Wednesday.